In the previous video, we proved the closed form of first order recurrence relations by mathematical induction, and today we're going to expand on that. We're going to now prove the closed form of second order recurrence relations, which is a very slightly different procedure. Okay, so let's have a look. Using mathematical induction, prove for n greater than or equal to 0. Here is our second order recurrence relation. It's called second order because it's got an minus 1, i.e. the previous term, and an minus 2, the term before that. So it's got the nth term is in terms of the n minus 1 and n minus 2, so it's second order. We have two initial conditions here, a0 and a1, and then we have our closed form here, i.e. the nth term, an, is in terms of stuff which is not an minus 1 or an minus 2. That's called the closed form there. Okay, so basically what we're going to do is we're going to prove it by induction. There's the same 4 steps, but they are slightly different, so let's get going. Okay, so step 1 is our base case. Now, because it's a second order recurrence relation, we need to show that the closed form here, what we're trying to prove, is true for both n equals 0 and n equals 1, because we're given a0 and a1, so therefore we need to prove that it is true for both n equals 0 and n equals 1. So let's put n equals 0 into our closed form. That gives us a0 is 3 times 4 to the 0 add minus 2 to the 0, which equals 4, so that is equal to a0 there, so that's correct. And a1, putting 1 into our closed form here, is equal to 3 times 4 to the 1 add minus 2 to the 1, which gives us 10, which is correct a1. And so therefore our base case, n0 and a1, is correct. Okay, now our inductive step, our assumption step, step 2 is the assumption. Again, this is slightly different. What we need to do is we need to assume that it's true for n equals k and n equals k minus 1, i.e. we are assuming that the closed form ak equals 3 times 4 to the k add minus 2 to the k, I'm just putting k into our closed form, is true. And we're also assuming, putting k minus 1 in, that ak minus 1 is 3 times 4 to the k minus 1 add minus 2 to the k minus 1. We have to assume both of those. So basically how the induction is going to work, just as a slight bit of an aside, as we have proved that it's true for n equals 0 and n equals 1, if we can prove that it's true for ak and ak minus 1, i.e. these, then it is true for n equals 2. And then we can say, well, if it's true for n equals 1 and n equals 2, then it must be true for n equals 3. And then we can go, if it's true for n equals 2, n equals 3, then it must be true for n equals 4, etc., etc. So that's the idea behind having the 2 base cases and the 2 assumptions. So step 3, what we need to do now is the inductive step. Inductive step. We need to show that it's true, the closed form, for n equals k plus 1, i.e. we need to show that a k plus 1 equals 3 times 4 to the k plus 1 add minus 2 to the k plus 1. That's just putting k plus 1 into the closed form. And this is what we need to show. Okay, so what we do now, as in the previous example using the first order, we use our recurrence relation here. So basically this is how we're going to prove it. So our recurrence relation, let me just write it here again, is 2an minus 1 add 8an minus 2. That's our recurrence relation. Okay, so putting in n equals k plus 1, letting that gives us a k plus 1 equals 2 a k add 8 a k minus 1. That's from the recurrence relation. Now we are going to use these 2 assumptions here, and we're going to put them closed form into here. So that gives us a k plus 1 equals 2 times 3 times 4 to the power of k add minus 2 to the k. That is our ak closed form that we've assumed is correct. Add 8 times, now we input the ak minus 1, 3 times 4 to the k minus 1 add minus 2 to the k minus 1. That is our ak minus 1 closed form that we have assumed is correct. And now what we need to do is we need to manipulate this in order to prove that. So I'll try and keep it on the screen if I can. Okay, so that equals 6 times 4 to the k, add 2 times minus 2 to the k, add 24 times 4 to the k minus 1, add 8 times minus 2 to the k minus 1. That's just expanding all of that out. And remember, what we need to do all the time is we need to look at what we're trying to prove. Okay, so let's get rid of these k minus 1. So that equals 6 times 4 to the k, add 2 times minus 2 to the k, add, well, 24 is 6 times 4. So that gives us 6 times 4 to the k minus 1, which is times 4 to the k. Add, well, again here, 8 is minus 4 times minus 2. So that will be minus 4 times minus 2 to the k. And now what we can do is we can add these up. That equals 12 times 4 to the k minus 2 times minus 2 to the k. And now just looking at what we want to prove, I've tried to keep it onto the same on the same page. 12 is equal to 3 times 4, so that is equal to 3 times 4 to the k, which is 3 times 4 to the k plus 1. And minus 2 times minus 2 to the k is minus 2 to the k plus 1. Add minus 2 to the k plus 1. And hence we have proved that on the assumption of what the closed form of k and ak minus 1 was, we have shown that ak plus 1 also satisfies the closed form there. And then all we need to do now is we need to write our conclusion, which again is very slightly different. Basically, as true for n equals 0 and true for n equals 1, remember we had 2 base cases, and as true for n equals k plus 1, given true for n equals k and true for n equals k minus 1, then our statement is true by mathematical induction. And that gets us our extra mark on the test. Okay, so you can see that basically this is a fairly similar question to the first order. It's just very slightly different, but once you've got the hang of it, these should be relatively straightforward marks in an exam. Okay, well, I hope you found this useful, and I hope you get one of these on your exam and get full marks on it. If you'd like this video, please like it and subscribe to the Gresty Academy YouTube channel. Thank you.